Hey guys, Mr. Grant here with a challenge video for 8.4, more of an in-depth explanation of asymptotes with this one. So here we go. So looking at this problem, we know from our notes that because the power of x is bigger on the bottom than on the top, that we have a horizontal asymptote at y equals 0. But let's think about why that is to start with. Let's take a look at the graph. We can probably think like, okay, when I plug in numbers that are really big into this, like big positive, big negative numbers, it's going to be 4 over a big number, and that's going to create a very small decimal number. And so it's going to get really, really close to 0. So let's take a look at that. So on Desmos here, I've got that in. We've got our two vertical asymptotes, right, because the bottom would factor to +2 and -2 because of the difference of squares. And I want us to let's focus more on what happens at extremely large values, right? And what's also going to happen here is if I start zooming out far enough, eventually this graph just looks like a flat line at y equals 0. Now we don't even have to get necessarily that far away from the graph in order to get really, really super close to 0. So like -15,000. We're going to focus on that number. Kind of an arbitrary number, but it's going to work out really well. So if you notice, the further I zoom in, the decimal numbers on the right-hand side for the vertical scale are getting to be really, really small. Like right now, one big square is 0.1, and I'm basically still right on the y-axis. I have to zoom in incredibly close. I don't even know if I can zoom in close enough on this one to start seeing any separation. Okay, there we go. So, look at the scale there. -1 times 10 to the -7. That means that one of the big squares, that's like 5 little squares, is 0.000001. So incredibly, incredibly small. And if I put my pointer on there, at -15,000, that's a super tiny decimal number. I mean, that's basically 0. So what we can say with a lot of confidence is at large x values, that this is pretty much the same as the line y equals 0. That is basically the same if I plug in a big enough x value into this, that it's pretty much 0. Okay, so, but it's also never quite 0. So that's why it's an asymptote and not like it doesn't actually equal exactly 0. Okay, so let's move on to this one. Now, looks a little bit different. Now we've got x on top and on bottom, so we just took that, that equation and basically added a variable on top. Still from my notes, I know that it should have a horizontal asymptote at y equals 0. Now, we'll take a look at this one, and then I want us to think about another way to think about these in terms of like these huge x values. So if we look at it, it's fairly similar looking. It's a little wonky, not exactly symmetric, but it's still got the same vertical asymptotes at -2 and 2. But if we start plugging in bigger and bigger values of x, what's actually happening here? Let's say if I plug in 100, right? So 100 plus 4 over 100 squared plus 4. Well, that's going to give me 104 over 10,004. And that's pretty darn close to 100 over 10,000. If I were to estimate it, I would say that those two things are pretty much the same, right? Like you could round 104 to 100 and 10,004 to 10,000 in most, scenarios. Okay, so now what if I plug in 1,000? So 1,000 plus 4, 1,000 squared plus 4. And so that's going to equal 1,004 over 1,000 squared is a million, so 1,000,004. And so now that's, again, I can round that. That's about the same as 1,000 over 1,000,000. Oops, I can write. And so what I'm saying here, I guess, is that at sufficiently large values of x, this plus 4 and this minus 4 really start to become insignificant, right? The difference between a million and 4 and a million really isn't that much. Even 1,000 and 4 and 1,000. And what if you start plugging in like 10,000 and 10 and a million and 10 million? That 4 becomes more and more insignificant. Oh, I just realized that I added 4 in the denominator instead of subtracted, but it's basically the same thing. Okay, it'd be 9,996 and 999,996 instead. So we'll say that this is a plus 4 just to, so Mr. Ground can save a little face. Okay, so basically what we're saying here is that this x plus 4 over x squared minus 4 for sufficiently large values of x, so at large x values, is basically equal to x over x squared. Well, x over x squared, that reduces to 1 over x. And for much the same reason as before, that's basically going to be at large values of x equal to 0. Now, if we look back at the graph, we can actually see this, how close these two become. So if we do 1 over x, now in the middle here, they're not very similar, right? They don't look, you know, they're pretty different. But let's go back to that negative 15,000 and see how close they are. You know, I start backing up, and now it's like you can't really tell where one begins and the other ends anymore. And I haven't even really zoomed out all that far. All right, so there's about 15,000, negative 15,000. So if we start zooming in there, notice how small the decimal numbers on the scale, the vertical scale are. We're already, you know, one big square, one little square is 0.00001. And so if I keep zooming in, can I even get close enough? Okay. So I finally got close enough. I mean, we're talking about like super small scientific notation times 10 to the negative fifth. So like 0.0000001 for our scale. If I look at the two values here, you know, negative 6.6649 times 10 to the negative fifth, and get the purple one, negative 6.6667 times 10 to the negative fifth. Those are incredibly, like microscopically close to one another. Okay, so let's take a look at one more situation. What about this guy? So the last example here. Now this one, because the top has an degree that's higher than the bottom, we know that there's not a horizontal asymptote. So let's see what's going on with this goofy one. Get rid of that. So we said this was now x squared plus 4, and the bottom was going to be x minus 4. Well, now we got something different looking. Let's zoom out and see if we can, there's the other half of it, if we zoom out a little bit. Now notice that this one, it's kind of like the ones that we had before, but now it's on a slant, right? It's kind of like a slanted asymptote, and we didn't learn about that, did we? Well, oblique asymptotes or slant asymptotes are a real thing. You could imagine drawing a diagonal line through the middle of this that would match that, match this rational function. So if we go back here, one thing that I want to, like the point I want to make with this is x squared plus 4 over x minus 4. This is, this is literally equal to, and now we're not just talking about at sufficiently large values of x. This is for real equal to x squared plus 4 divided by x minus 4. And this is a problem that we can do. Like we did this in chapter 6, right? We could use synthetic division and divide this out. The 4 goes in, 1, 0 because there's no x, remember, and then a 4 at the end. Bring down the 1. 1 times 4 is 4. 0 plus 4 is 4. 4 times 4 is 16. And we've got a remainder of 20. And so this is legitimately equal to x plus 4 plus 20 over x minus 4. Well, guess what happens to this 20 over x minus 4 at sufficiently large values of x? It basically becomes 0. Now, again, it doesn't completely become 0. It's always just a little bit off from it. But it's basically the same thing as 0. So that means that this function is pretty much equal to x plus 4 plus 0, or just x plus 4. And so if we go back to the graph, we can plug in x plus 4, and you can see how well, outside of the area in the middle, when you get sufficiently large values of x, these are basically the same thing. And if we zoomed in, I don't want this video to go too much longer, so I'm not going to zoom in at 15,000, but you could imagine it's going to be, really that microscopically close once you get, just a little bit away from the origin. When you start to get into the thousands and the millions and stuff, it gets very, very close.